Okay, so thanks everyone for coming along to the AFMS seminar for this week. So it's my pleasure to introduce our speaker for today, Dr. Melissa Kozul from the University of Melbourne. So Melissa completed her PhD here at the University of Melbourne in 2018 under the supervision of Associate Professor Daniel Chung and Professor Jason Monti. And she spent the last 3 years or so doing a postdoc in Norway with the thermofluids group at NTNU, and she's recently come back to Australia and been a research fellow at the University of Melbourne. So please take it away, Melissa.
Thank you very much for the introduction, Kat. And I'm so pleased today to have this opportunity, this online opportunity to present some of the progress that we've made on this problem. And this work really would have not been possible without my co-workers listed here. So this is truly an international effort. Firstly, beginning with myself and James Dawson, who is my supervisor at NTNU, Pedro Costa at the University of Iceland, and Luca Brandt at KTH in Sweden. I'll start with a little geography because I think it's perhaps not so well known where Trondheim is, and I certainly didn't know where it was even when I signed my contract, to be honest. So this is Norway, a map of Norway, which is very long and skinny. Oslo's down here, and most people live in the south. Here is the Arctic Circle, just pointing out, and of course we know beyond that point at certain times of the year you don't have any night or day, and it really shows it's just an illusion. And Trondheim is halfway up here, and it's so far north that you can actually see the northern lights there in the winter. And this is a photo of the beautiful main building at NTNU. So as a preview of the work I'll be presenting today, so the title is The Aerodynamically Driven Rupture of a Liquid Film by Turbulent Shear Flow. Here is a liquid film. It's in yellow. We have perfectly flat surfaces at times equal to 0, and it's been sandwiched between turbulent gas phase layers, and the velocity fields of those gas phase layers are projected on the back sides of that box. Now, in time, as that gas flows over the liquid film, it first creates small dimples in it, and these dimples then grow slowly at first, and then they become larger and larger, and then quickly growing to eventually rupture this sheet, like this. And this work actually is all contained in our recent publication in Physical Review Fluids, so there's many more details in there that's in addition to what I'm covering today. So where does this problem come up? This is just one example, aside from being a fascinating problem on its own. This has very real industrial importance. And this is a prefilming airblast atomizer as used in aircraft. So here I've highlighted in blue where the liquid fuel is pumped out. We have airflow coming from left to right through here over the top. Oops. Let me go back. Sorry about that. We have airflow going over the top here and from the other side, and we have the liquid fuel being pumped in here in blue. And it serves to then, at the lip of this air blaster, this atomizer, you get this liquid fuel sheet being torn up and turned into droplets for the next stage, which is of course the combustion chamber. Now, this is a very complicated geometry, 3D geometry. It's actually symmetric. And so in order to understand this problem, to study it, people often conduct simplified 2D experiments. So converting this axial problem into a 2D problem, because it is locally, at least, largely can be understood as a 2D problem. And again, here we have the airflow. So from left to right on either side of this plate here, and the liquid is being injected here upstream. It moves downstream to the edge of this atomizer, where it gets, again, as before, turned into droplets. Now, what's actually happening here is, obviously, we have turbulent boundary layers forming on either side of this atomizer. And we see here at the end what's happening if we zoom in, that atomization occurs in this shear zone between the two airstreams. Now, what manufacturers really want to know is something called the SMD, so the sort of mean diameter, which is basically describes the spectrum, or the average size of particles that you get of droplets that you get into the combustion chamber. Now, this is very important because for clean combustion and for efficient combustion, you want this fuel to have atomized as fast as possible into the smallest possible droplets, both for efficiency, as I said, and also for NOx emissions. So in order to reduce this, you want this sort of mean diameter to be as small as possible. Common practice today in industry is that correlations are developed for each type of atomizer, and they're tuned to work for that atomizer and for those conditions. And sometimes these correlations aren't even dimensionally correct. And so what our work seeks to do is to develop more first principles driven understanding, a priori understanding of this rupture and then atomization onto atomization of the liquid sheet. There have been many efforts on this problem, clearly, and some of the first studies were of linear stability analysis. So this goes back to 1953 with Squire, and this is actually at this interface. So here again we have liquids, and we have, so this is a reverse problem, but it's just a transform. So here we have the liquid actually moving, and the gas phase is at rest. And this is not turbulent. This was just studied for quiescent flow, but basically a shear-driven disturbance of this gas-liquid interface. And this was studied. So Squire was the first to study this Kelvin-Helmholtz instability actually that forms on this gas-liquid interface. He was the first to study this problem with the ingredient of surface tension. So sometimes it's called the Squire problem or the Squire instability. And we see the sort of things they're trying to predict, these length scales that come out, and also the growth of the disturbances themselves. Now, this is a very important work, and people have learned many things from it. More recently, this was a study that combined linear stability analysis of this problem with VOF simulation, so gas-liquid simulation, sorry. And they concluded basically these dominant modes in the linear regime, so there's small deformations, so within the linear regime, are clearly not the ones that are responsible for atomization, so they're not enough to actually rupture this sheet. Even though they found good agreement at early times, these in the linear regime, these disturbances were just not the ones that were actually tearing up the liquid surface. So how can we go about studying this problem more systematically? Some inspiration we take from this study of Desjardins and Pitch. Now this was for a reverse problem, so it was for a turbulent liquid jet issuing into quiescent air, but some of the ideas proved to be very relevant, very useful for our study. So again, disturbance of the gas-liquid interface here. And in their case, as I said, they have the turbulence coming from the liquid side. But nevertheless, we have a disturbance happening on this interface. And what they proposed, but didn't study systematically, is the fact that this disturbance, this initial disturbance, is then amplified, or through a sort of feedback mechanism with aerodynamic forces is basically increased, and that this sort of mechanism is what causes the more severe deformation of this interface. And so back to our problem, we need to look at this film that it's subject not to just sheared flow, but it's subject to turbulent sheared flow. And what this setup that I'm going to describe in our work will seek to do is to really accurately take a film and place it between fully developed turbulent shear layers, and to really accurately capture that turbulence that's coming from that engineering setup, and how it deforms the sheet, as we just saw on that little sketch before. Now, the title of this work is called The Rupture of the liquid sheets, or liquid film, sorry. And we are focusing here on what's called primary atomization. So the initial rupture, or the initial deformation and rupture of that sheet. Following on from primary atomization, you obviously have secondary atomization, where those ligaments that form from that initially ruptured sheet or liquid jet then turn into smaller and smaller particles, which then leads to that SMD that I was talking before, that average droplet size. However, that process of secondary atomization is much more universal, and sort of the correlations that exist work better for that part. The really challenging part, and where we believe this work can make a difference, is on this early period that is highly dependent on the types of deformations that originally occur. And we're seeking to find a first principles way to describe this early rupture, this early atomization process. So how do we form our simulation? We start with a precursor channel flow. Where do we get these boundary layers from is probably what I should have asked. We start with a precursor channel flow. So here is a fully developed channel flow with the periodic condition in the streamwise direction. So the flow is from left to right. And we have walls here until it runs to being fully developed. Then we stop the simulation. We have our fully developed shear layer. We then split the velocity field in the middle like this. And then if we just watch this little triangle, I'm now going to invert these shear layers like so. And in the middle of here, this is where I'm going to place my liquid film, and it's going to have a starting thickness of WL0. And just mindful of this, what's happening with this shear layer, we see that we've preserved the periodic boundary condition here at the top and bottom. So we haven't violated any rules or anything. And we of course have the periodic boundary conditions still in the streamwise and in the spanwise direction, so out of the page. And we have continuity across this shear layer. So again, this part that was originally at the wall, so zero velocity, is now facing the zero velocity of the film. And so this is a very, very simple and very easy actually setup to run. And we have sort of minimal moving parts to study this problem in a very fundamental and clean way. Okay, so now that gives us our velocity fields, and of course for the two-phase simulations we also require an initial condition for the VOF, or the volume of fluid, for this multi-phase simulation. That's pretty easy. Again, we have this initial thickness for the film. When we're in the film, so this black region, we set the VOF to be 1, and when we're outside of it, we set the VOF to be 0. Just a few computational details here. So this mthink method, so a way to capture that interface, was used, implemented by my colleagues at KTH. As I mentioned before, the problem is triply periodic. There's no forcing. Once we set up this problem, those shear layers decay in time as if they were coming off that edge of the atomizer edge. As if they were being moved downstream in time, they would decay because they're not being forced anymore. So analogously, we have the decay of these shear layers, which we'll see in a moment on our mean velocity profiles, that they decay in time. And we've used a uniform mesh. We use typical channel dimensions, and we've taken, so back to that paper, Desjardins pitch, that we saw that little diagram for of the amplified deformation due to aerodynamic forces. We've borrowed some of their parameters here. So this is the Weber number. This is the liquid and gas density difference, and the viscosity. Gas phase Reynolds number, this is our really important ingredient here. And we've ranged from 180 up to 393 for the friction Reynolds number. That's of the precursor channel flow simulations, that then this obviously then decays in time. Now this is very important, that we get something that is fully turbulent to be representative of those industrial flows. On the other hand, we believe this Reynolds number, even though it can be seen as low, is sufficient, because what we really want here is that these near wall, this near wall cycle that's established at the wall is representative, and that is established at the Reynolds tau of 180. So this is, we believe, adequate to study these flows. Okay, so this is how we got this visualization from the beginning, but I have many more pretty pictures coming up, so this is not the only one. So now we can get an idea, a bit of qualitative understanding of what this flow is doing once we start the simulation. So time is equal to 0. We have perfectly flat sheets, and our bulk flow from left to right. So this is just the VOF in time. So we have it deforming, really not, we can't even discern it at the beginning, but in time these deformations, they grow and they amplify slowly at first, and then really accelerating, if we see now in the next couple of time steps, very fast now, the film is really getting torn apart by those shear flows. And we see we have all sorts of things happening. We have thickening here. We have these little lobes, which cause big disturbances to the flow, locally. And we also, as we'll see in a moment, have flow reversals. And here's where we stop the simulation. So as I said before, we're interested in the primary atomization phase. Streamwise velocity. So these are our starting velocity fields that came out of our channel flow simulation. Here we have the liquid film. If we look at, I've used a creative color bar here so that we can see a few different things. So here, blue is for zero velocity, so that's our starting film velocity. And as we go in time, we can see again, not much happening at the beginning. And as these structures flow over the liquid film, it's deforming it much more. And just before I show that picture, here we can see the emergence of some reverse flow regions. So that's in white here as the deformation starts to come out. And to contrast this very quickly to what it looks like at a higher Reynolds number and how important it is to get this Reynolds number effect in there, we see that at a higher Reynolds tau, we see many smaller scales being introduced to the problem. The sheet is very much more convoluted at this stage. And we also have more regions of flow reversal. And here in little circles, I've highlighted very high speed regions, as I said, over those little tips that were forming, those little lobes that peeled off from the main sheet. Back to our, this is the RE tau 180 case. So again, reverse flow at a later time and high speed regions over those tips. Finally, the pressure. As we saw on that little sketch, the pressure is going to be a very important ingredient in understanding the aerodynamics of this problem. So obviously it starts off not very interesting, and then in time we see something interesting emerging. So we see now pressure highs and lows slowly emerging as the film deforms. And we start getting these high and low pairs. Now, if we just stop for a moment and look one of these segments, this could remind us of the pressure field over an airfoil. And so we're going to come back to this a bit later and see how we can use ideas from classical aerodynamics to understand and quantify the deformation and rupture of this film. So back to the full fields and getting really big pressure differences now across that film. Okay, so now something more statistical. So we can look at plane average statistics in time. So these were cut throughs in 2D, and now we're going to look at our little sketch down here. We're going to look at average quantities in the film normal direction, so in Y direction, over each of these planes. So we see this red plane, we're going to average quantities and have a look what they look like, so that we only get quantities as a function of Y, like so. And starting with the VOF, so where the liquid is on average in the domain. This is the channel center line here, and we have the vertical dimensions of the box along here. Now, of course, when we start at time is equal to 0, we have this perfect step profile that we put into the liquid. So we've got either we're in the liquid, so we're in the film, which is at 1, or we're outside of it. And as time moves on, this starts to smooth ever so slightly at the beginning, and then more and more as we go on. And we see that the liquid is starting to be moved on average very fast now. So we saw from time to 3, time to 4, how quickly that happened now. So this is pointing to really an accelerating process, which we'll see in some quantities a bit later. how this liquid film is being smeared away from that original location on average. So if we think back to how that film was corrugated, this is the average view of that. And this is really when the film's broken up already. Average streamwise velocity. So again, here we have this periodic boundary condition that was preserved here. So they were points that were contiguous in space before, and now they're contiguous by this periodic boundary condition. And here we have the mean streamwise velocity in the film is 0 at the beginning. Well, all velocity components are 0, but within the film it's 0, and we have the shear layers on either side sandwiching it. And so we have no forcing, so these shear layers in time are going to decay, and we see slowly again at first how momentum is transferred into the film with time. So it's no longer 0, or slight, it's being dragged along with the shear layers in time. Again, slowly at first, we see this is the decay of the shear moving this way in time, and quicker as we go on. And now we see a significant rearrangement of the momentum in our box. So that was a view, that was an average view along the y coordinates. So now let's take a look at, well, we've looked at it from the side now, we've looked at it from the side beginning, and now we'll look at what's happening to the film from the top view. So this red surface, we're going to take a look at how this film deviates from the initial film height. We see at early time, so this is time is equal to 1. These deformations are quite disorganized. If we think back to that original 3D render that I showed, it was quite just the little ripples on the top of the film surface were quite disorganized at the beginning, but they become more organized, or they become larger with time. And here red will be positive deformations and blue are going to be negative deformations. And now the interesting thing is to start to compare how this varies across the different cases that we did. So moving on, so this was a thin film, this was a thicker film, and on the right here we have a higher Reynolds number. So immediately we can see that a medium film will serve to delay these kinds of deformations. And the higher Reynolds number will hasten the process. So we have much larger, they're all using the same color scheme, much larger deformations for, they're all at the same time post beginning of the simulation. So all at times equal to 3. And so we start to see the influence of both on the size of these deformations and on the how large they are at a certain time. This film is actually already ruptured at that time. So moving on to these two cases that have made it to the next time, we see now that at this point we have deformations that are arising at a similar sort of scale at this time, so but at a later time. And here we still have quite small deformations at times equal to 4. But moving onwards to times equal to 6, we now have deformations that are roughly the same scale as these guys at earlier times. So here, just beginning, we start to see the influence of both film thickness. So this is the thickness of this layer at the beginning, and also the Reynolds number. So that was of the gas phase the gas phases on either side, the turbulent gas phases. Just have a sip of water. Okay, now I've shown you lots of pictures, essentially mainly of what's happening. I think we're starting to get an idea of what this film is doing in time. How can we now quantify this? So we come back to the pressure back to the ideas of using aerodynamics that I sort of promised at the beginning. So for this, we're going to need a few more different types of analysis that I'll go through now. So quantifying the film's evolution. So this is a film that's at a certain, probably halfway through its simulation. And we see in the Streamwise direction, streamwise dimension, this is the full field, and in the span, so away from the film in this direction. Now here we have the dotted lines are signifying where the film was at the very beginning. And as I said, this is at a later time when it's deformed. We can point out or start to pick out the minima and maxima of this deformation, and many if statements later, because there are many things we need to control for, we can pick out these points so that they're not too close to each other, and so on and so forth. And these dark points are where I needed to basically add the minimum or maximum to the other side because it wasn't present on one side of the film. So as I said, many if statements, we can pull this out, and then we can segment the film like so. And this analysis is going to become very important in a moment. From this analysis, we can start to pull out things like the deformation at these, using these minima and maxima, thinking back to that first sketch from Squire, and track these deformations from the original location of the film. We can also pull out the length scale, so this lambda, so we can have multiple measurements of this on each side for each time, and track what this lambda is basically in time for our simulation. So this lambda is the wavelength, so analogous to like a sine wave, we take, being inspired from that linear analysis, we take differences between minima and maxima here to define a lambda, so a length scale, streamwise length scale that's emerging. Diverging just for a few moments from the pressure, I promise I'll get back to it because it is the most interesting part of this work, I believe. Looking at what this lambda does, so this has been scaled with the original film thickness, looking at what this, which doesn't change by the way, looking what this lambda does in time is very interesting. So it's, as we saw, those initial deformations tend to basically stay there, this would say, and basically once that lambda is set, it seems to just be amplified. And so this points to the idea that those initial deformations are very important, and it is important to get them right, which is part of the motivation of having representative turbulence in that gas phase on that perfectly flat film, such that those deformations are coming out only from the gas phase. Again, comparing to the thick film and the thin film, this is also true for the thick film especially. The thin film is there's a bit of perhaps, it could be scattered. These are all from single simulations only. But we see it locking into a fairly constant lambda at late times, especially obvious in the thick film. Now you might ask, why don't these curves start at times equal to 0? That would be because we can't measure it. So I don't accept a lambda measurement that's not of a certain magnitude. So to be sure it's there. So that's why they don't. It takes much longer for those deformations, if we remember from those top views, to emerge in that thick film case. And so then we need to wait longer for them to come out, and then longer still for them to be measurable in a robust way. And finally, adding on this curve for the higher RE tau, again, we have a pretty constant lambda measurements. So this is the streamwise wavelength in time beyond some early measurements. Back to our pressure fields. This is now I guess the main story of this talk. So we've using our segmented analysis, so we can from what we saw before, if we remember, I just pulled out one visually of the little segment that reminded us of an airfoil. Now we have a systematic way to segment this film. And so what we seek to do is study, and these are the pressure fluctuations. I seem to have lost my my label here. What we seek to do is now, from that picture from Desjardins pitch, we seek to analyze that lift force, that vertical force, coming from from the pressure field. And if we do that, but to do that, I just want to convince you that is the main force in this problem. So I'll have one more diversion before we get back to that. This is showing the viscous stress on the surface of the film. So it's integrating the viscous stress on this surface, on both surfaces of where I'm just dragging my hand, and on the bottom surface, we integrate this viscous stress over the surface of the film. How does this look? The answer is it's not very big. So this is now I've recast. So this is just this was the total viscous force, but this is just the X component. I'll look at each component sequentially. So this is just the X component written as a coefficient. Yeah, so we see that it's quite small, and it's also decreasing in time. So this is from the original parasitic drag from those turbulent boundary layers on either side. So in the X direction on either side of the liquid film, and it decreases in time. And because it's set from, if we zoom in, if we look into this point, we see all these three cases. They started at the same RE tau, and so they have the same coefficient here, whereas for the higher Reynolds number, it's slightly higher because that's set from the original U tau at the wall, so the original viscous stress at the wall in our channel simulations that then goes to the surface of that film. So it's quite small, and it's decreasing in time. Now for the other components, it's even smaller. So it's really not playing a big role in this. So this is Y, and this is in the Z direction. It's really not playing a very big role in this problem. And so these figures just serve to show the minor role of parasitic drag in this problem. And so we're really now free to focus on the inviscid forces, or the aerodynamic forces on our liquid film. So back to this, now I have my label back. So these are the pressure fluctuations of over the liquid film at a certain time post beginning of the simulation. However, now we finally see the real use and power of this segmented approach, because we see they're alternating. And so if we were to, over each segment xi, were to just integrate that lift force, so the vertical, so the pressure over the surface of each of these segments, if we were to just sum this up, what would happen is this would be roughly zero, because this problem is all symmetric in that direction. We would get something, this lift force basically being zero. Now we can see that that's sort of not a false picture, but that it's hiding what's really happening, because we can see these neighboring alternating highs and lows that are really tearing this sheet up. And yet we get, if we just integrate this lift, we'll get only zero. So in order to not have that effect masked, we need to take the absolute value, obviously. And we call this now, instead of just the lift force, we call it the cumulative lift force. So it's the combined effect of the lift over each segment as we move down our film. So rewriting this as a lift coefficient, we're going to look at what this looks like in time versus for our different cases. And note, this vertical axis is 10 times larger than what I was showing for those parasitic drag coefficients. So they are really very small. So starting with one of our cases down here, so perfectly flat film, no lift force. Obviously, this is at zero, so we don't have this effect. And it starts off slowly. Again, we have these tiny deformations now coming out of our liquid film, and they grow now. Now it starts to really grow quite quickly, and we find our lift coefficient is growing even more rapidly now. And as it really tears up, we see this lift coefficient. So now we have these really pronounced pressure highs and lows on each side of the film, serving to increase this coefficient quite rapidly. Comparing how this looks for our thick and medium film cases. So we see that this is a similar process in all the film thickness cases, but we find a significantly delayed process for the medium and then the thick film even more so. And we find this process is hastened for the RE tau, high RE tau case, which comes as no surprise, given the visualizations before. But what we want to do now, going back to our first problem, how do we parameterize? How do we parameterize that early primary atomization of the liquid film? This is something now that we believe is really this cumulative lift is sort of tracking or describing how this film develops and these forces over the film. And now we would like very much to be able to collapse these curves as best as we can. So as a first attempt, we can use the bulk as a velocity scale, use the bulk velocity of those precursor channel simulations. So naught is for the precursor, so at times equal to 0. And the liquid film thickness at the beginning. Now this is forming a new timescale here. This helps a little bit with the beginning of when the uptick starts to happen, when the deformation starts to happen, but it's not really collapsing. It's not really successful down at later times. So we believe this shows that this isn't really the right velocity scale to be using. So moving on, talking about the important role of inviscid forces here, we've been looking at the lift force, but we also have the lift-induced drag force here, from which we can form something called U tau d. So we can form a velocity scale from this lift-induced drag force, and we can try this, as we believe this might be more indicative. And we find that this really collapses the curves much better. And this U tau can be understood as a type of mean streamwise inertial force over the film. And so this now does a better job of collapsing our curves. Even at later times, it's not perfect, but it's doing much better than using the bulk velocity. We think that was the wrong velocity scale. And this might be going a step further to describe a local velocity scale that's relevant. So contributions, haven't gone very long here, but contributions of this work. We've simulated with liquid film sandwiched between fully developed turbulent gas phase layers, and we believe that was important in order to properly represent those engineering flows. We need to properly represent that turbulence. And as we saw, once it locks into a certain length scale, it's going to stay there. So it's important to represent those correctly. We also saw the role of the Reynolds number as it changed, how much it changed the ensuing deformation and rupture of the liquid sheet. This is an efficient temporal setup that still allows us to study the important physics right at that the gas-liquid interface. And so far we've looked at 2 film thicknesses and 2 gas phase RE tau, which would have been sort of unthinkable if we'd tried to simulate at these resolutions, simulate the whole plates and that whole flow. This is just honing in on that liquid film rupture due to that gas phase turbulence. So we find the amplification of initial disturbances leading to rupture is obviously delayed with the thicker film and accelerated for higher RE tau. And we were looking at cumulative lift force because, as we'd shown, we'd understood that this problem can be really understood the role of just by looking at inviscid forces. And so we were looking at something we called a cumulative lift force that was permitted due to this segmented analysis that we were using. And it was collapsed with some success using a velocity scale derived from this dominant. So again, dominant, I mean dominant here is the dominant inviscid forces, here the dominant lift-induced drag force. So this last part is really going back onto that original problem of that industrial atomizer and going our efforts to get first principles understanding of how this deformation and rupture happens from parameters in the problem, physical parameters in the problem. Now, outlook. All of these simulations were conducted cold, as you could say, so there's no role of temperature or evaporation. Obviously, the industrial problem is with hot gases, so this code recently has been extended to include, by my collaborators, extended to using an evaporating film. So we have phase change now through the boundary. So we believe that's going to be a very fascinating problem to study. Also, how this changes as the film deforms, and how these rates of evaporation might change due to different thicknesses again, or where might this be hastened locally, or that sort of thing. Even further on, this code has been another. I can hardly keep up with them. Another extended again with a low mark approximation. So this allows then one to simulate large density changes in the gas phase without worrying about acoustics. So that's what the low mark approximation permits. And further afield, we've used this for the film setup. So here I've got again a little sketch of our problem that we've used. But another question that we'd like to look at is how this converts to a deep liquid setup. So using a fully turbulent boundary layer over something that's much deeper, and how importantly also how this would change compared to using that film setup. Because what we're really interested in is what happens to these physics at the gas-liquid interface. And an important question there would be how that differs between the film and the deep water setup. So I will leave it there, and I welcome any questions that the audience might have.
Great. So thank you so much, Melissa, for that talk. I really enjoyed it. Your simulations are just, to me, they seem very well thought out and kind of innovative. So it was fantastic to see those. I will open the floor up for questions. I think we already have someone willing to ask a question. Tushar, if you want to go ahead.
Hi. First of all, thank you so much, Melissa, for such a nice talk. It was very good. I just have a very trivial question, just out of my curiosity. So in actual prefilming atomizers, the RE tau would be comparable to what you used, or it would be larger?
It's probably higher. It's probably higher. This is, again, where we're limited. This was so the higher RE tau here, we're talking almost 3 billion grid points already. So it's, I am limited, we are limited by that. Although, as I mentioned, that because the near wall cycle is already established there, we think it's still representative. So it would be higher. Yeah.
Okay. Thank you so much.
Okay, do we have other questions from the audience? Feel free, if you're in the audience, to put your hand up too, and we can call on you as well, or type into the chat. While people are thinking, I have a quick question, Melissa. So this was, your simulations are 3D, right? You have the across stream, but you kind of have more 2D structure. Is that the way to interpret this?
Yeah, definitely. We have, because that's the dominant direction, that's the shear. The shear is in the dominant direction. One thing that I do want to look at, and actually before I get onto these more exotic codes, one thing I do want to look at is looking at a bigger domain in the Streamwise and Spanwise, so that I can study more of the Spanwise deformations, which are important. But yes, definitely you get that dominant wave happening, and that comes from the dominant shear direction.
Okay.
But there are deformations, there are definitely dimples that are happening across the span as well.
Yeah, that was my question, was going to be, what happens if you increase the span?
Yeah, that's my question too. Yeah.
Awesome. All right, anyone from the audience?
I might go next. Very great talk, thank you. I just have a question about your interface. when you initializing your liquid phase, you mentioned it's going to be 1 and 0.
Yeah.
How do you decide about going from 1 to 0? Is it, I guess it's not the step function.
It's a very tight blending. Is that what you mean? It's across the, yeah, but it's not an exact step function. The computer doesn't like that. So it's a very how can I say? Yeah.
How do you decide about that thickness? Like from 1 going to 0?
We haven't
influence your breakdown process.
Yeah, we haven't. I mean, that's a good question. We haven't. I think that the other effects are bigger, like the film thickness and the Reynolds number. I think that is changing it more. Basically, because it takes a little while for these deformations to even happen. So that very, very first condition, it changes quite quickly, right? So yeah. So I don't think that's the deformations don't come out that quickly from the turbulence. So the real deformations, they don't come out that quickly. So but we haven't studied that in any systematic way, but I shouldn't think it would be a big difference, especially compared to the other effects that we have here.
Okay. And one more question, getting back to Kat's question. In the span-wise direction, how big is the domain in these simulations?
Yeah, so it's sort of typical channel. I think I have some backup slides here, but this doesn't tell you about that. It's like it's half the direction. So we have H, which is the original channel half height. It's 6 in the Streamwise and 3 in the span.
Okay.
Yeah. But a next simulation I would love to do with this cold code, because it's a lot cheaper than these other guys, would be to double the Streamwise and spanwise direction, just to see that we don't have see what comes out. I don't think there'll be big differences in like physics. We don't get very many measurements of that spanwise dimension. Whatever comes out, we don't get very many measurements of it. So in order to that be better converged, it would be good to repeat this in a bigger domain. Mm.
Thanks.
Anyone in the audience? Otherwise, I have a quick question, which was just, you mentioned early on in the talk that you saw like a little bit of flow reversal in some of the kind of maybe just before it ruptures.
Yep.
Is that, I'm just trying to physically understand what's going on there. Is it like I don't want to call it an eddy or a blockage? Okay.
Yeah, I would see it as a blockage.
Okay.
It's basically like what's the word? A barrier almost, right? It really stops it. If I go back.
Yeah. Okay. And enough that it actually reverses direction. Yeah. Okay.
Yeah. So it's almost. I mean, you see, it's almost trapping this flow, right? Locally. But here you can see a very. It's almost at 90 degrees, right? It's stopping this flow. So yeah. So the density difference is 40 to 1, and it's stopping the flow moving. So part of all this aerodynamic study is really understanding this liquid film almost like a membrane. That's for all intents and purposes, I'm studying it. All the analysis that I did was as if it was a solid surface or a membrane. So I can pick out the interface exactly and integrate the pressure over that. So. And that's sort of what we see coming out here.
Thank you. Okay, any last questions from the audience?
So yeah, I just have one more.
Yes.
Just another thing which came to me. So in the beginning of your talk, you mentioned giving some reference that some experiments were done, probably. So what quantities could be experimentally measured, like which could be compared with simulation?
That's a difficult question. Obviously, in numerical work, we seek to, if it's possible to match things to, or to compare things to experiment. This is a very challenging. I think Daniel knows about this. Very challenging to measure the velocity fields in the vicinity of this film, right? And it's impossible. or practically impossible to measure the pressure fields, which is the main story of this work. And so that's why we think in this problem, you know, this is where numerical tools can really help, because this pressure field, which turns out to be a really great way to understand this systematically, is unmeasurable essentially. A lot of experimental work has focused on visualizations, so they can see you know, lots of photos of atomizing sheets, and they also measure things like the frequencies, which comes out of the linear analysis. That's the sort of thing. We could do that in theory. Maybe that's a thing to try, to measure, you know, a type of frequency, essentially how fast these are coming by. But we don't have very much time here. These simulations don't last for very long, so I'm not even going to get a converged sort of measure of that. Yeah.
Thanks for the information, Melissa.
No worries.
I think Daniel Duke, you've got your hand up.
Hey, sorry. Thanks, Melissa. Great presentation. I'm really sorry I actually got distracted by a student for a couple of minutes, so I missed part of the discussion, and I apologize if you talked about this while I was away for a moment. But really nice, and it's nice to see people, nice work, nice to see people working on this really nasty problem, liquid film and liquid sheet instability. My question is the mean question that I always ask everyone when I see work in this area at conferences and stuff, which is that we know linear stability theory does a really bad job at predicting ligament and droplet size in these kinds of flows, because like you said at the beginning, the initial Kelvin-Helmholtz Rayleigh-Taylor type instabilities you get end up bearing no relation to the size of the droplets that you end up getting. So there's a disconnect there. The question is, and this is a hard one to answer, I guess, is there any hope for nonlinear global stability analysis in these kind of problems, given the huge computational cost of doing a simulation? We know that the local linear doesn't work. Are we ever are we ever going to get anywhere, in your opinion, with like global nonlinear stability analysis, or do we just have to? Do we need interface resolving simulations in order to understand what's going on here?
Yeah, I haven't done that kind of analysis myself, so I'm probably not really qualified to answer that question. But this is definitely, the work here is definitely trying to get to something from first principles, right? And we think that this pressure, which hasn't this aerodynamic effect, which has been suggested by theoreticians a lot, but hasn't been studied systematically. It's always sort of pointed out as a thing. I think people can appreciate that if you have this mound, that it's going to, if we go back to, no, it's not. It's after this. But if you have a deformation in the gas liquid interface, that it's going to be increased by aerodynamic forces. But we haven't seen studies of it systematically. So we think this is the right direction of seeing it like this, and looking at more global. This is a more global quantity over the whole film. So we are hopeful of this kind of global thing, and we think that the pressure is the right way to study it.
Yeah, thanks. It'll be really interesting to see whether, for example, like global stability analysis using data sets from these kinds of simulations will be able to tell us anything new about what's going on here. At the point where the curvature gets really sharp and you actually start to get that initial primary atomization happening. Yeah, thanks. Nice work.
Thank you.
Okay, any other questions from our audience? All right, if not, I might draw this to a close. So thanks again, Melissa, for your excellent talk. And, Sharon?
No, just want to thanks.
Oh, okay. That's a thank you as well. And hopefully see everyone next week for our next AFMS seminar. All right, thanks.
Thank you.
Thank you.